Hey Jacob, for some reason I don't have audio. That's fine because I'm doing the thing today. So there we go.
Yeah.
That was me. All right, let's go ahead and get started.
Yeah. I think our session's going to be recorded from now on.
Oh, what?
Just make again. I said I'm guessing our sessions are going to be recorded from now on. Like
Oh,
with no one
yeah.
else. Just yeah.
Yeah, I'll probably end on like Friday or something. All right. Anyways, thank you to our sponsors: GPS, AXL, Griffin Engineering, and Vision Metals. Alrighty. So first thing, so the thing that we skipped off on was we were creating a sketch that models the intake, and Jacob edited his sketch that he made. So here's so I'm going to show you the one that he made on last time we did a YouTube video, and then also the one that he made yesterday, so that you can copy that one. Sorry, Autodesk is kind of slow. All right, so this is the one that he made yesterday, and this is the one that he made. No, I'm sorry. This is the one that was from the last video. This is the one that he made yesterday. And the difference is that instead of having the piston, this piece be the piston, so that this can move down and up like that. Instead, this piece right here is the piston. So when it extends, this basically will move down. So what we're going to do is I'm going to let you copy this, and then we'll see how the ball works in this system and constrain some stuff. So here we go. So basically, when the ball is like this, and the ball, when it's like that, there, when it ball will, so this represents the ground right here. This line does. So as the ball comes this way, it's stopped right here. It's picked up by this wheel, because this piston will be fully extended. Then the ball will be constrained to this face. So, and it will also be constrained to that. So as it moves up, it will basically do that, and then slowly come into the robot like that, and under the intake, and then it'll be inverted. So you don't have to do that, but that's kind of showing what's going to happen. And then this is just a piece of burst frame, and so is this. So this will move in and out like that. So what we have to do is find a piston on your master card that can do this. And Jacob, you already found the piston, right?
Yeah, that's what I sent to you. And it's like that's the notification was.
Let's see. Okay.
Just mention like which sketch to mention, like which of the versions you're using.
Yeah. So we're using, I guess we're going to use version 2. So download that. And we want we're running Excel version 1 right now. So that all we're doing is this sketch right here. Oh, and when it's all the way up, it will be inside frame 2. So first thing we're going to do is open that thing we just downloaded. Sorry, I did that too pass. This is, you can type in this link in MasterCard, and then it'll give you give this again. So, try to open it from downwards, like we usually do. Be sure to click all files. And I want to put this in, I'm saving all of the files, which is in CAD class intake. All right, so this is good, except that, wait, let me show something. Double acting. So I have a question about this, Jacob. Don't we want it to be usually in, so that when the game starts, it's automatically in?
Yeah.
This is a double acting piston.
Yeah.
Wait, but
Double acting just means that like single acting means that like only only one direction. Like I think just pushing out is like a force, and then like retracting is just like taking the air pressure out. But double acting, like instead of like when it's retracting instead of just like taking the air pressure out, it like actually like also uses force to retract it. So it like it basically just like puts a force both directions. So like you can.
Okay, I think I remember that. That makes sense. So we want this piston to be able to move in and out in our animation. So what we're going to do is actually make an assembly, and then basically animate this piston. So sorry, press saving. All right, here we go. So we're going to ground, we're going to get 2 of these and then ground this one. Actually, only 2 of them. So now what we're going to do is go back to our files and click on this and copy and paste it. We want this to be the, you can keep that product name so we don't get confused, but we want this to be the actuating portion of the piston. So now what we can do is place the actuating portion of the piston here. We're going to open it and then delete that. And all we want is the actuating portion. Let's see. All right, there we go. Save that. So now what we're going to do is go into this one and then delete everything except for the actuating portion. I mean, everything, sorry, that happens. Basically just like that. Okay. And then what we can do is do a maximum minimum constraint. So, but first what we're going to do is do that to this. And then, so now this is on the, going like that. So now what we can do is constrain this, and it can go, we want the maximum to be -5, and minimum to be 0. I make the minimum -5 and the maximum 0. There we go. So now it goes in and out like a normal piston, and I have a little animation that we can use in our actual. So this is going to be the piston. All right. So next thing we can do is start using the sketch to, make the 3D orientation of this. So we're going to need some VersaFrame. So we can go in here, and instead of having to download it again from the internet, we've already downloaded it. So what we can do is just copy this, paste this, and so we can just rename this because it hasn't been put in assembly. If it was inside of an assembly, we wouldn't be allowed to rename it because the assembly would be looking for a file of that name in a folder. So you have to keep the instance of that file, but you can copy and paste it if it's in the assembly. So this is going to be the back intake support, vertical intake support, and we're going to have to make this piece of VersaFrame 5 inches long. So what we're going to do is start a sketch on this end, project the geometry, and then extrude it. I'm going to do a cut extrude. That's weird. Oh, sorry, I did that way too fast. So look, so the problem I'm having is that for some reason it's telling me to do it in millimeters. But I know that this piece is 59 inches long. So what I'm going to do is convert the document to millimeters. So you can go to document settings, units, convert it to inches, sorry, length inches, apply. That way, Autodesk automatically converts the length of this from millimeters to inches. So if you measure it, it's still 59 inches long, but all of the units are in inches now because we just converted it to inches. So I can now extrude this 59 minus 5. Alright, there we go. Now we have our tiny piece of VersaFrame. Next thing we want to do is go ahead and close all these out. And go back to the sketch. Next thing we're going to need is an 11-inch piece of VersaFrame. So all we have to do is go to our previous piece of VersaFrame, this one, and then click. And then this is the we can call this the moving intake support, because this will be moved by the piston. And we want this to be 11 inches long. So all we have to do is click here. And that's the good thing about doing the subtraction problem. I did 59 minus 5, so basically I'm putting the length that I want right here. So all I have to do is take 11 and it becomes 11 inches. That way you don't have to deal with like parameters, which is something that you can look into if you want, but it makes it a little easier for us. So this base piece of VersaFrame right here is the drivetrain. So that's already done. And something that I realized just now is that this drawing is not really accurate. So what we're going to have to do is change this. So you already know that this is 90 degrees. So we can do a parallel constraint. But we're going to have to open the little bracket that we're using to see the other offset, so that we have the right one. So this sketch, this 1.125, represents the distance from here to here. That's good. Wrong information. 1.625. So we have to change that one too. This is
it's the dimensions from like the middle holes to
that.
Oh
yeah.
hole. Yeah.
Well, wait. Oh, because in your sketch, this line is the middle holes.
Yeah. Oh. Because it's like at the bottom.
Yeah.
That's like where it would be mounted, I guess. So like.
Okay. So this one is. Alright, so never mind. I was wrong. So Jacob's sketch was correct on that one. On this one, we want to do 1.25. And right now, it's just measuring this distance, but we don't want that. We want the x distance. So what you can do is click delta, because these are the delta coordinates. no, these are the Cartesian coordinates. So this is the x distance. You can see it's 1.25 along the horizontal plane. You can see that it's x because down here you have your little Cartesian plane indicator, which is x, y, and z. So this is the x-axis, 1.25. Next thing, so we basically just gotta put this 1.25. And instead of making this a 90-degree angle, that kind of, when you have a ton of things, right now, we don't have like an insane amount of dimensions. But if you did, you want to just use a parallel constraint. And, okay, that was good. Yeah, you would want to use a parallel constraint because that way people could look at your drawings easier. I don't know why this is breaking. Okay. And this is just the same 2-inch circle. Maybe, okay. I don't know. That's weird. Anyways, so it's still 11 inches. That offset is correct. And now what we're going to do is we have all of our reverse frame pieces. Now what we can do is start putting them all in an assembly. So this is going to be the main intake assembly. And whenever you name a main assembly, see we have like our hexagon on our inlet piston, just name it intake assembly so that everybody knows what it is. Don't name it something crazy. So that's annoying when people are trying to look at your CAD. So what we need is that, and we're going to need that piston. Sure, we're going to need that one. And then just click once, and it'll place everything that we have. Oh, my bad. Don't need these files because we already have it right.
Jonathan.
Yeah.
So I think like in the sketch file when you added the like offset
Yeah.
downward kind of, I think you should put in like I guess like because you made the offset like downward, we have to extend the like overall 11-inch piece of Versa frame
Yeah.
so that like where the wheel is the same. So I think it has to be like 12.25 inches now because you did 1.25 down. So that like where the wheel
Right.
was before is the same.
Yeah, that makes sense.
Okay.
All right, cool. Thanks. So this is all right. Next thing we're going to need to do, so we have our left mechanism wheel, but we're also going to have to put in our right mechanism, which, Jacob, did you get that? Oh, yes. Oh yeah, that was that weird one where they were different colors. We can just change that in the assembly to make them black. Is that way? Not a good fancy black. The next thing is, let's see, everything. Oh, the versaplanetary motor so that we can spin this. So what we're going to do first is kind of orient. We're going to base everything off of this piece, which if you want to go back to the sketch, is this one right here. So basically, what we're going to do is constrain this piece. Don't worry, we're going to ground something, but we also have to constrain it like that. And we actually wanted to go to this point so we can use 80-20 L brackets, which we will do in a second. I'm going to do that one. We also want to constrain it to this plane. And now it can move like that. So we have to constrain it to this plane. Now this piece, is essentially grounded, but to make it so that people understand what your assembly is based off, you just want to go ahead and ground it. The reason I did that is so that if we show you, make all these planes visible, it's oriented in these planes rather than just like somewhere off kind of crazy. So all right. So next thing we're going to want to do is copy this, and we have to make sure that these are flush with each other in that way, and we want them to be flush in this way. Okay. So now we have to figure out the distance between the two. Luckily, we have our entire robot on CAD, so we can just reference it. But if you didn't, you would just estimate the distance, and then once the whole robot comes together, you might have to change it. So this will take a while. It's a whole robot. Okay. So what we're doing is replacing the intake assembly, which is this one right here. So what we have to measure is the distance between this bar and this bar, which is 15 inches. So I'll move this over here. So basically that means we have to constrain this and this and make it 15. There we go. So now this piece is constrained in this plane. Next thing we got to do is place our next piece of versifying, which is this one right here. Just 10 inches long. But this one has to be able to rotate on an axis. So we're going to have to do something interesting here, which is going to be putting a shoulder bolt into the first frame. So what we have to do is basically, sorry, this is kind of hard to explain. So I'll make this assembly invisible. So don't mind these chains. Basically what we're doing is putting a bolt through here so that our bolt through right here so that our VersaFrame can rotate back and forth. And that way, once this piston actuates forward, this piece rotates on this axis. So to do that, what we're going to do is over here, and we're going to use an 1818 shoulder screw. So basically, what you have to remember when you're picking this out is that, we'll just pick this piece of version for example. It's a 1x1 VersaFrame. So you want to keep you want to definitely have these walls in there. So the shoulder bolt has to be smaller than 0.8 inches. You also want it to be larger than about, let's say, 0.25 inches. Because there could be a considerable amount of force on this bolt. Because so your intake is obviously going to be hanging out of your robot. So if another robot, what other teams like to do is accidentally come and crash into the side of your intake, which will basically mean there's going to be a ton of force on this bolt right here, pushing it the other way, and on the piston, which is very rude. So to counteract that, we got massive shoulder bolts. So what we're going to do, what I'm looking at is right here, is the shoulder diameter. So I said that I wanted it to be in between 0.8 and 0.25. So I'm going to make it a half-inch shoulder bolt, which is if you think about it, that's a pretty big bolt. That's not going to break anything. So what we want this to do, and this is kind of in place of like a bushing or a bearing, because we don't need those things because this shoulder acts as its own bushing. So what we can do is get a 2-inch shoulder bolt. This is the shoulder length. Go over here and save it. the next thing we're going to need is going to be 3/8/16 line, because it looks better if you have a bolt with a marker. That's how you should CAD, especially things like this. So here, and you'd be tempted to buy a high-strength nylon insert lock nut because it sounds cool, but you should actually go ahead and buy either a medium strength or a low strength, because we only use our robots for like a few hours in total. So this is like a super long robot that you've used for years and years and years. But just buying a low strength steel lock nut is fine, and like they're never going to break for what we're doing. So I said that it was a 3/8/16 thread. So you can go over here, click save. Right. So what we can do is open these and put the .ipt files in our assembly. Right. So save that, and save as. We want to put this as a. Oh, that's right. My computer's automatically set up to a project file, so it's saved automatically, but you will have to save it to the folder that you're saving. So many things that you want to do. So basically, we can go back in here, and we want to open. We have our huge shoulder bolt and our nylon screw, nylon lock nut. Okay. All right. So now what we can do is go back to here, and we know that this piece is actually not going to be that long. We have to extend it yet again, because this piece has to stick below this, because in your robot, you want the nylon, you want the shoulder bolt to be in the middle of this piece of VersaFrame, so it has strength on both sides. So for that, we're going to need to extend it an inch. So this would be, instead of 12.25, it would be 13.25. So here we go. Next thing we're going to do is go back to our assembly and start constraining this. So we definitely want our piece to be, we want this face to be constrained to this face. And we can, I'm crazy. We want this face to be constrained to this face, so you don't have to drill a new hole. You can just use one of these existing holes and widen it out. So next thing we're going to want to do is do some fancy constraining. So the thing that we care about is this hole, because we're going to use that for a bolt. So if we go from here to here, we know that there's a 2-inch piece of VersaFrame between this, below this on the drivetrain. So right now, it's taking the center of this hole to this face. So we want it to be an offset of 1 inch. That way, it'll be able to go like that. Next thing we have to do is constrain this to this. Okay. So basically, we want to have this rotating like that. And for this, I think we're going to use an axis that should align with our sketch. So an axis is basically the exact same thing as a plane, except for it just goes through a hole. So our axis is right there. So if you want to make it longer, you just have to very carefully click on this dot. It's very hard. Okay, does not want to go. So what we're going to do is go back over here. So we know that if we go into this sketch and extend this line 1 inch and make this line parallel, this line, make this angular dimension 1 inch. Note that this is basically the center of the hole. So if we have our axis right here, we also want to have a constraint right here. So that would mean that the dimension from here to here would be the same 10. So what I'm trying to do here is make our object be able to rotate on an axis and basically do a cool animation so that when we're presenting this, we have a way to show people what's actually happening. So this piece right here is represented by the middle of this. So we have a 10, it'd be 10 minus 0.5, so it'd be 9.5. So it'd be from this face to this axis would be 9.5. Okay. So basically now it rotates like this. But sorry for all the math. Next, we're gonna do the exact same thing over here, and we're gonna have to create another axis on that one, and constrain this face to this face. Next, we're going to constrain this axis to this face, and offset at 9.5. And then come up here, and then do another constraint of, let's see. So which plane is this not constrained in? Looks like this one. Okay, so for this one, you can look back at your constraints by clicking the plus. So I did a mate there. That's correct. I did an offset of that down 1 inch. So from this face to this is an offset of 1 inch. Alright, now our pieces should go to rotate. Well, we actually want them to rotate together. So what we're going to do is click this and click this, make them rotate together. There we go. So the next thing we're going to do is bring this crazy axis over here. And since we don't really need our axes anymore, we can just make them this one. All right. So the thing about this is that you don't want to have it rotate. You don't want to have this piece dependent on your bolt. Because what happens if you change your bolt or your bolt size, you're going to have to end up redoing all of the constraints. So you want to have them based on the axis instead. So what we're going to do next is put our bolt in. Right there. And can paste. And in the real world, you would make these holes larger and to fit the 0.5 inch shoulder. But in FRC, you don't have time to do that because if you change the bolt size, you don't want to also have to change the size of the hole and deal with all of that stuff. So the next thing we're going to do is find our walk line. And a good way to do that is to just highlight over where you think it is. See it. So we need 2 of these. So then we don't want them to rotate. So if they do, Autodesk will have to think about whether they should rotate them. So basically all we're going to have to do is just put it on this. And it looks like it'll just be like floating there, but actually there'll be another piece of versiframe right there, which, once we put this in the full robot assembly, we'll be able to see that. And there we go. All right, so now we have it rotating like that. So the next thing we're going to do is put these in. So what we're going to do, so if you were going really cheap, what you could do is just put one on each side and just basically only have 2 of these. But since these are so they're like $2, we're going to have 4 of them so they're strong. Because this piece on our robot, this is the only piece on our robot that's ever going to be outside frame perimeter. So we want it to be basically one of the strongest pieces on the robot. So we don't want to go cheap on this. So that face will be flush with that one. And basically just putting this on like that. And this will be able to house bearings, which we're going to put into our assembly next. So there we go. All right. All right. So now when you move this up and down, this moves with it, which means that it's fully constrained. So we're gonna copy and paste 2 more of these, because we want 2 more, and then we're gonna do the exact same thing on the other side. Now you could technically mirror this entire assembly, but that is not a good practice. Because when you mirror something, it saves another copy of it in your folder. So if I mirror my entire assembly, I would have all of these files, and then after it, it would say mir mir space 1. So what happens if you want to edit your design and you want to edit only one side of it and put some more components in? Then you have to delete all of the mirrored files and then mirror everything again, which is a huge pain, and you don't want to have to keep doing this. In the real world, you could probably mirror something like this because you probably wouldn't edit the CAD like 20 different times. But in FRC, we edit CAD a lot because CAD is kind of like a cheap way to prototype stuff in our team. So there we go. Now we have this piece. Well, next thing we're going to do is just kind of move all this stuff out of the way. We're going to do the roller bar next. So to attach the roller bar to these pieces, what we're going to need are some bearings. So we already have the bearings downloaded, but I'm not going to show you how to download them again, because that's what you're going to have to do. So we're going to go get these from Inventor. And we're going to need a 0.5 for here. So thing that's important about these is the bore. And the bore is basically the center. It's the, so like this one right here, 8mm round ID, means that the middle of this is 8mm wide. This 1/2" hex ID means that this has a 1/2" hex on the inside, which is what we want. So you can click on this and download it. Oh, a thing about AndyMark, most of their CAD files are placed right here, right on the product page, but some of their CAD files are placed on this massive database of step files, which is an absolute pain to look through. See, there's like every single file they enter. So yeah, at some point you'll have to look through that, but that's how you get files if they aren't placed on there. So the next thing we're going to do is actually open our hex bearing. And we want to put it in GrabCAD 2020 class 17. Sorry, I accidentally clicked escape. Save it. Put it in the folder that you're putting all these other files in. Alright, there we go. AndyMark and sheet on this now. So what we're going to do next is save this. And save, and then put it, and then if you click place, it's in this file, in this folder. There we go. And we're going to need 4 of these. And for this, we're going to use the same insert with a lock constraint. We're going to insert it on this flange, this face, and that flange. And so here to there. All right. And we're going to do the same thing. And if you had a lot of time, what you could do is orient these so that all of their pieces are the same direction. But that's a little, we don't really need to do that. It's going to waste your time. So we're going to save it because we have a lot of stuff in here. Next thing we're going to do is map out our Thunder hex. So our Thunder hex needs to go almost to our front printer. So make these bumpers invisible and measure, I'm pretty sure it's like 28 inches. Yeah. So we want our thunder hex to be 27 inches long to be safe. So what we're going to do is download some thunder hex. I know I think we already downloaded it. Yeah, in our previous assembly we already downloaded it, but we're going to do it again. So, and we are going to, so you can basically run thunder hex. So we use half inch because it's stronger than 3/8. But you can basically write an 18 inch or 36 inch. So this says it's out of stock, but it'll go back in stock in 2021 in the next season. So an important thing about buying this stuff always goes out of stock. They can never, I don't know what the problem is, but they can never make enough of it. So it's really good to stock up on this in the off season if you have enough money to buy some. So we want a half inch 36, half inch hex 36. We'll download that. Go back over here, open it, and then put it in the same folder that we had. So previously we haven't really been naming our files because they're really specific, like pistons and stuff like that. With this, before we put it in the assembly, we can name it. We can name it thunder hex because everybody knows what that is, instead of having this ridiculously name it just. Alright, so place this in there, and we want to go into this file, and we know that it's 36 inches long. We start a sketch there and project the geometry, and then extrude it. 36 minus 1. And there we go. Now we have a 27-inch piece of bursary. And we don't trust this abstraction, you can just measure it. Next thing you're going to do is use a plane to put this in here. So you can create planes in part files like that, or you can create them in assembly files. And you want a mid-plane between right here and right here. This will save us having to measure. So the next thing we're going to do is create a mid-plane between this plane and this plane. Okay. So what we're going to do is constrain here, here, here. Now, if you go to the right view, you can't get it off of that plane, which is exactly what we want. So next thing we're going to do is use this bearing to constrain that face, and then constrain that face. So now we have, when this moves down, within this. And since planes can be kind of annoying, and what if you have an assembly with like 50 planes? Like if you go into our final robot assembly, and if I turn on all the planes, there's like a million. So what a shortcut, instead of having to make every single one visible, is you just click View, Object of Zero, and then All Work Features, and that just erases everything. Well, it makes everything invisible at the same time, which is convenient. Alright, so next thing we're going to do is put on these wheels right here. So we have to be careful about orientation. So this is a right-hand wheel. So when this is spinning, it will push the ball to the left. This is kind of complicated. And since this is kind of hard to see, what you can do in View also is you can click Shade with Edges. Now you can see all the edges, which is kind of helpful. So we're going to put this wheel on the very outside right here. And then shrink it to that one too. Now it can move like that. So what we're going to do next is put this right here. So now when you move this back and forth like that, we'll go in. So we're going to put one more of these wheels right there. Same thing. And something that we have to be careful about is whether the ball will hit this piece right here. Because in real life, in CAD, in like NF or CAD, you can just keep it there if it's going to hit it anyways. Because you can just tell your build team, hey, you're just going to use the bandsaw on this and cut it down. So we want this wheel to be, let's say, maybe a 3-inch offset. Well, yeah, sounds good. And in the actual, when you're actually testing this, it'd be very good to move this around and see what happens. But as I was saying with the offset, I'm going to make this invisible so you can see. If a ball runs into this, it will touch this wheel and not this bracket, which is exactly what we want. And if in CAD it looks pretty good, but I mean you can see that it's a little tight. So if you wanted to in the build season, you could trim out or cut this out with a saw to make it work better. But we don't need to do that in CAD. So the next thing we're going to do is get our left wheel and put one of those. And this is going to be in the opposite orientation of our right wheel. So I'll put this one first. So we want these are pointing towards the center. So we want these to also point towards the center. On this. Okay. To make it easier on myself, I'll just do this constraint first. Now I can see which faces go to which faces. There we go. All right, we got our first wheel, and this is just a copy of it, so we can put it into. All right, so let's face the right way. We're 3-inch offset, and put this in. And in the build season, when you're actually ordering stuff like this, like these wheels, stuff goes out of stock really fast. So you want to make sure to maybe order 3 right-hand wheels and 3 left-hand, just in case you want to put another one right here. If it turns out that's good. But since this season is already passed, kind of already know what's going to happen, and that this design actually does work. So I'm going to put another one in here, a little bit closer, because you need a few of these pushing the ball towards the center, because that's really important this season, because the balls like to stick on everything. So I'm going to constrain this wheel to a 3-inch offset to this wheel. And I'm just going to kind of act like this bar isn't even there, because that's how the ball will think of it. It won't, because it's not going to touch this, it shouldn't touch this bracket. So it'll think 3-inch, 3-inch, 3-inch. And that way, it'll be very consistent across the board. So we can do there. And then we also want to do the same 3-inch offset right here. Forgot to type 3. So a shortcut you can do is go right here, and then if you just click on Make 33, this little thing pops up, and it says offset D54, which is dimension D54, and then you just type 3. That way you don't have to delete the constraint and waste your time doing it. So here we go, and you want to go to that face. All right, cool. So now we have our 6 mechanism wheels. So next thing we're going to do is make all these black. That looks cool. So this won't actually change the color in the actual part file, but it will just change it into a single file, which, you know, is good. So we don't have a bunch of crazy colored wheels. So the next thing we're going to do is put a bunch of these omni wheels. So basically the ball will be directed towards the center and be pushed in with these. So the black, so there's like, let me go this for a second. So if you go to, and then let's say, there are different durometers of wheels. And the durometer is basically just the, let's see, it's like how squishy it is. So the darker durometers, like the gray and the black, are harder than the green ones. So what we want to do is put a green one in the very center. So that it works better. So, all right, I forgot to say this. This is kind of the intake that we're basing it off of. So it's got some mechanism wheels and then 2 omnis and then green. And we've seen this to work well in the build season, in the competition season too, not just on that video. So what we're going to do, it's probably the last thing I'm going to do. I'm going to put these wheels on. I already constrained it. So from there to there. And then you want this offset to be about 2 inches. It's kind of weird. Let's see, so I'm going to see what the constraints are on this by clicking that. There's a mate there and a mate there. So instead of having to deal with this weird constraint, what you can do is just constrain it based on the middle. So I'm going to do a mid plane between this plane and this plane, which is this tiny little plane. Okay. Let's see if they make theirs right. All right. Okay. So I have to make this bigger because I have to be able to see it in the actual drawing, in the actual assembly. Sorry. If Autodesk can make these little tiny circles slightly bigger, this would be so much easier. Alright. How about I just make an offset plane that's 0 inches? Aha. There we go. Now it's larger. There we go. Now we can see it. That's kind of a sketchy way to do it. Okay. So we want our planes to be visible now, so you have to check their visibility. Oh, it's a big thunder. I don't know if you can hear me. Alright. I don't know. This is weird. Alright. What we're going to do is just do all these constraints, because for some reason, this omni wheel is not letting me scoot it back and forth on the x-axis, which is kind of strange. So let's say I want this plane to this plane. Jacob, do you know why it's doing this?
No, I'm confused too.
So
I mean, try like putting like no constraints on the wheel and like just doing the plane first.
yeah. I tried to do it like 4 different ways.
Yeah.
Oh no, it's not Autodesk. It's my computer. It's like super slow. Let me wait a second. Check. Alright, I don't know what's wrong with my computer. I think it's probably the Wi-Fi or something. It's like it's like barely even working.
Oh my God, I don't know what's happening.
Okay. Oh. Okay. Let me try it again.
I'll just go ahead and save just in case.
Yeah, definitely save it right now. What's happening to my computer? there's a large storm and AT&T decided to end my Wi-Fi usage. Okay, well, I guess that's all we're doing for today because, oh my goodness.
Okay, I mean, it did save, so like.
Yeah, and it's
okay
almost
now.
time to be over.
Yeah.
All right, good thing I got that saved. That was kind of crazy. All right, so, oh man, this is really laggy. So, on Friday, Jake's gonna finish up, put his piston on, put the motor on, do some more Omni stuff, and hopefully it actually works. And then, yeah, and then we'll be able to put it in our full robot assembly. Wow, I'm surprised it actually loaded that. And then take out this bad intake and put in our new roller bar intake, which will hopefully look better. Oh, and yeah, in the actual build season, we're gonna have to put in some new electrical because note to future freshmen watching this video, never put your electrical in stacks like this. It's a massive pain. So you can't get to anything on the lower stacks, even if you have hinges or whatever. But anyways, all right. I think that's all for the meeting because my computer's about to die. So, all right, guess we'll see y'all on Friday.